Hi there! You're listening to the Science of Everything podcast, episode 22, Our Place in the Cosmos. In this episode, we're going to look at the location of the Earth in relation to, well, the cosmos, that is the wider universe. So I'm going to start off with discussing the Earth and the Moon as a system, and then move up through the solar system, nearby stars, the Milky Way Galaxy, and right through to the universe in its entirety. And each step of the way I'll be describing how the Earth fits into the whole and what structures we are embedded in, and so on. So you can get an idea of how the Earth fits into the big picture of things. So, let's get into it, and we'll start off by talking about the Earth and the Moon. The shape of the Earth is not perfectly spherical. It is very close to that of an oblate spheroid, and an oblate spheroid is basically a sphere that has been squashed from top to bottom. So if you can imagine an orange, for example, and then put your hand on top of it and squash it down a little bit so it's fatter in the middle than it is from top to bottom, or in the case of the Earth from pole to pole. That is an oblate spheroid. So the Earth's pretty close to a sphere, but it bulges a bit around the equator. The reason for that is because the Earth is rotating, and so as it rotates, it sort of flings the middle parts of the Earth around the equator outwards a little bit, basically owing to the angular momentum. That difference is rather small, though. It's only about 43 kilometers. The Earth is only 43 kilometers longer from one side to the other than it is from pole to pole. And given that the diameter of the Earth is about 13,000 kilometers, 43 kilometers is a rather small difference. Even Mount Everest, which is something like 8 kilometers tall, and the deepest crevice in the ocean, which is in the Pacific Ocean somewhere near Japan, which is something like 10 or 11 kilometers deep, those are the greatest extremes in terms of elevation in relation to the Earth's surface, and those are really tiny in comparison to the total size of the Earth. So the Earth is very close to being a perfect sphere. If it was to be shrunk down to the size of a marble or something like that, and you were to pick it up and handle it, you probably wouldn't detect too much of a deviation from a perfect sphere. Now, as you probably know, the Earth rotates around its central axis once per day, and that's why we have day and night, because for half the day we face one side of the Earth faces towards the sun, and then for the other half of the day that side faces away from the sun. The Earth rotates towards the east, and that's why the sun appears to rise in the east and set in the west, because the whole Earth is really rotating in the direction of east. Just as we rotate about our own axis once per day, the Earth also orbits the sun once per year, as you probably know, and that's what gives rise to the year. Now, because the year and the day are really quite separate concepts, and there's no particular reason one should be related to the other, the orbit of the Earth around the sun is quite separate from the rotation of the Earth about its axis, there is not an exactly even number of days in a year. So although we say there are 365 days in a year, there's actually 365.2564 mean solar days in an average year. So basically there's an extra quarter of a day for every year. That is, for each time the Earth goes around the sun, it rotates about its axis approximately 365.25 times. So there's an extra quarter of a day there, and that is why we have leap years every 4 years. An extra day thrown in to make up those 4 quarters of a day that have accumulated over the past 4 years, because otherwise the seasons would get out of whack with the calendar. It's actually quite complicated orbital mechanics and the way that calendars and times and things are adjusted to keep track with the seasons and so on, but that's probably best left for a separate podcast. Now, the Moon is relatively large in comparison to the size of the Earth. It has about 1/4 of Earth's diameter, which is the largest relative size of a moon to planet in the entire solar system. Pluto's moon Charon was larger. It had about half the diameter of Pluto, but it's no longer considered a planet. Of course, Pluto is now a minor planet. But anyway, the moon is still quite large compared to the Earth. It's also relatively close to us. It's only about 385,000 kilometers away, which sounds like a lot, but when you consider that Earth's diameter is only about 13,000 kilometers, that means the Earth's only about 32 Earth diameters away. So that's really very close in astronomical terms. So just to give you an idea of magnitudes again, the circumference of the Earth, that is the distance around the Earth's equator, going in a complete circle once, is about 40,000 kilometers. And so if you were to drive around the Earth about 10 times, that would be the equivalent of going to the Moon. So the Earth is fairly large in comparison to the distance between Earth and the Moon. Now, the Sun is much, much further away than the Moon. It's about 150 million kilometers away. That's something along the lines of 500 times as far away as the Moon. But interestingly enough, although the Sun is 500 times further away from Earth than the Moon, the Sun is also 500 times larger than the Moon. So they appear almost exactly the same size from Earth, and that's why we have solar and lunar eclipses, because one basically moves in front of the other on occasions. They're not exactly the same size because actually the Earth moves in its orbit is not perfectly circular, so sometimes it's a little bit closer and sometimes a little bit further away from the Sun. Similarly, the Moon moves back and forth a little bit in its orbit as well, so sometimes you can actually see a little bit of a little bit of the outline of the Sun around the Moon in an eclipse, and that's called an annular eclipse. So it's not true that they're perfectly matched in terms of size, but they're very close, which is interesting. Okay, so that's the Earth and the Moon. And the other big thing about the Earth, of course, is that it is the only planet that we know of, and certainly that is known to support life. And Earth is very unique. If you look at pictures of all the planets, Earth is easily distinguishable, even if you sort of weren't really familiar with seeing them, because it's covered with something like 75% water on its surface, and so it appears blue and green, whereas the other planets are largely clouds or rock and dust. So the Earth is very distinctive in that sense. So that's the Earth and the Moon, our very local area. Now we'll zoom out to the solar system as a whole. The solar system consists of the Sun and everything or all astronomical objects that are bound to it by gravity. That is, the gravity of the Sun attracting all the other stuff. The solar system formed from the collapse of a giant cloud of dust and gas approximately 4.6 billion years ago. So everything in the solar system at the moment formed from that cloud. Now the Sun comprises something like 98% of the mass of the entire solar system, and most of the rest of the mass is made up by Jupiter, which is the largest planet, and it's significantly larger than all the other planets. So I've heard the solar system described sort of half serious, half tongue-in-cheek as the Sun and Jupiter plus assorted debris, because really everything else is just debris compared to the Sun and Jupiter. Okay, so there are a number of different types of objects that orbit around the Sun. 8 of them are called planets, and Earth being one of them. There are 2 different types of planets. There are 4 small inner planets and 4 large outer planets. The inner planets are also called terrestrial planets because they are made up primarily of rock and metal. They're relatively small, similar in size to the Earth, and have solid surfaces, and sometimes atmospheres. The 4 outer planets are much larger and are mostly made up of ice and gas, and probably do have solid core. Well, almost certainly do have solid cores, but those cores are much smaller than the total size of the planet and are sort of buried underneath massive, hugely thick atmospheres of highly compressed gas and ice and things like that. So the 4 inner planets, in order from the Sun moving outwards, are Mercury, Venus, Earth, and Mars. So Earth is the 3rd planet from the Sun. It's also the largest of the terrestrial planets. It's almost exactly the same size as Venus, just a little bit bigger. Mars and Mercury are a fair bit smaller than the Earth and Venus, about 1/3 the size of Earth approximately. So they're somewhere between Mercury and Mars are somewhere between the size of the Moon and Venus. Mercury and Venus both do not have any moons, and Mars only has 2 very small moons that are probably captured asteroids. And I'll talk about what asteroids are in a minute. So Earth is the only terrestrial planet that has a significantly sized moon. The orbits of all these 4 terrestrial planets are largely circular, not perfectly circular around the Sun, but largely circular. Like the orbits of the outer planets, they all lie on a fairly flat disk, or plane, called the ecliptic plane. So all of the 8 planets orbit the Sun in pretty close to perfect circles on the same plane. So if you were to move sort of up from above the plane, you'd look down and see them all orbiting around the Sun. If you were to move down, you'd see the same thing. They don't sort of crisscross each other and bend, go up in relation to the other, if you see what I mean. That's not the case for asteroids and other things like that, but it is the case for the 8 major planets. And one of the main reasons for that is because they all formed from the same giant gas cloud that collapsed in on itself 4.6 billion years ago, and so they all sort of merge into the same plane. And that's also why all the planets orbit the Sun in the same direction, because the initial rotation of the cloud would have been uniform in the same direction, and so all the planets were formed from that cloud, so they also rotate around the Sun, or orbit around the Sun in the same direction. Now, I'll talk about the 4 outer planets, which are also called the gas giants. As I said, they're much larger, from 3 to 10 times the Earth's diameter, so significantly bigger. All of them also have dozens of small moons. And in fact, they're still discovering many of the moons of the outer planets because many of them are very small. I think Jupiter must be coming up to having 100 or moons or something like that. But as I said, many of them are just tiny and not very interesting. Captured asteroids and the like. Just little pieces of rocks, basically. However, the gas giants also have anywhere from one to a few larger moons. Jupiter, for example, has about 4. Saturn, I think 5 or 6. And these moons, these larger moons, can be very interesting. For example, the moon Triton, which is around, which orbits Neptune, has geysers of ice on it, which shoot up a very large distance above its surface. Io, which orbits Jupiter, is the most volcanically active body in the solar system. And also Europa, another of Jupiter's large moons, is thought to have a surface covered with ice and covering an ocean of water which covers the entire planet or the entire moon. We're not sure about that, but that's the theory at the moment. And we can see cracks, what look like cracks in the ice, and there are theories that maybe life can exist or does exist at the moment under these ice sheets. But that's still speculation at the moment. But it's certainly very interesting, and I hope to see NASA probes headed there sometime soon. Anyway, so these moons of the outer planets are probably some of the most interesting places in the solar system. Okay, so we've got the inner planets and the outermost planets. Oh, one more thing about the outer planets is that all of them have ring systems around them, which are formed of relatively small particles of rock and ice, anywhere from like specks of sand to around the size of a bus or a house or something like that. So some of them are actually quite big. It's not like they're all tiny, but for the most part they're relatively small pieces. Saturn, of course, is the most famous for having large and spectacular rings, but actually all of the gas giants have rings. You can't really see the rings of Jupiter or Uranus very well, but they do have them. Neptune's are a little bit more visible. Okay, so that's the main bodies in the solar system. There are also objects called asteroids, which exist in large numbers throughout the solar system. They're particularly common in what is called the asteroid belt, which is a belt of these asteroids between Mars and Jupiter. Now, an asteroid is basically just a lump of rock, or sometimes ice, depending on where it's located in the solar system. The further you move away from the sun, the more ice you tend to find in terms of on asteroids and on the planets and so on. Anyway, they're just fairly small lumps of rock which orbit the sun. And the asteroid belt that lies between Mars and Jupiter has a total mass, which I think is somewhere around... It's only about 4% of the mass of the moon. So although there are millions of asteroids in the asteroid belt, its total mass is very small. The largest of these asteroids is called Ceres. That's spelled with a C, C-E-R-E-S. And it was actually, when it was initially discovered, it was thought to be a planet. It's smaller than the moon, but it is mostly round. It was discovered sometime in the 19th century, and since then several other fairly large asteroids that are also mostly circular have been discovered in the asteroid belt. And there's actually a NASA probe which is on the way to investigating a couple of those at the moment. Another belt of asteroids, which is located around the orbit of Pluto, is called the Kuiper belt. That's spelled with a K, K-U-I-P-E-R. And there's a lot more ice in the Kuiper belt because it's much further away from the sun. And it's also much larger than the asteroid belt, something like 20 to 200 times as massive. So it might have as much mass in total as the moon or the Earth. Although considering that there are probably billions of asteroids in it, that still is relatively small. Now, contrary to popular imagery, an asteroid belt, whether it be the Kuiper belt, the asteroid belt, or any others that you would find in other solar systems perhaps, are mostly empty. In movies you might see a spaceship or something dodging between the asteroids as if you can barely fit through, but that's not accurate at all. If you actually went to the asteroid belt and landed on one of these things, it's highly unlikely you would even be able to see another asteroid because they're so spread apart. There might be millions or even billions of them, but considering how large a space they occupy, larger even than the orbit of the Earth because they're further out than the Earth is, so they have a larger orbit. It's a huge space, and so it's very, very sparse. So the chances of actually, if you just flew randomly through the Kuiper belt or the asteroid belt, the chances of hitting an asteroid are very low. Now, in terms of measuring distance in the solar system and also in the galaxy, we use a measurement called the astronomical unit, or AU for short. Now, the astronomical unit is defined as the distance, or the average distance between the Sun and the Earth. So it's about 150 million kilometers. And that in turn is something like 500 times the distance between the Earth and the Moon. So that is 1 astronomical unit, the distance between the Earth and the Sun. Mercury is something like 0.3 astronomical units from the Sun, so it's much closer than Earth is. The Kuiper Belt, which kind of marks Pluto, by the way, is an object in the Kuiper Belt. It was originally thought to be a planet, but has since been downgraded because it's just realized it was kind of like Ceres. When Ceres was originally discovered, it was thought to be a planet, but then heaps of other bodies were found around that area in the asteroid belt that were very similar in size and composition to Ceres, so it was realized, yeah, it's not really a planet, it's just part of this belt here. Same thing with Pluto. It was discovered in the early 20th century, and then in the coming decades, particularly more recently, a whole bunch of other similar bodies were found in that area, occupying the Kuiper belt. One of them, in fact, that has been found is larger than Pluto is, and so it was realized, yeah, Pluto's not really a planet either. It's just one of these bodies in the Kuiper belt. So there was all this fuss about Pluto being downgraded from a planet to a minor planet, but in truth, it was just a reclassification that has historic precedent because that's pretty much exactly what happened to Ceres. Now, as I was saying, the Kuiper belt is about 50 AU from the Sun, so 50 times as far away from the Sun as the Earth is. And the outer planets are somewhere between 10 and 30 AU from the Sun, so quite a bit further away. I said before that Ceres and Pluto are now classified as minor planets, or also called dwarf planets. A couple of other bodies are in this population as well. For example, Eris, which is the Kuiper belt object, which has been discovered that's actually a bit larger than Pluto, and a couple of others. But really, there are probably dozens of bodies in the asteroid belt and in the Kuiper belt, maybe elsewhere too, that would fit into which would fit the criteria of a minor planet. So it's likely that we'll see more being classified into that category in the next few decades. Okay, so beyond the Kuiper belt, we don't really know much about what exists beyond the Kuiper belt because we've never sent probes really that far, and we haven't. It's hard to see that far away. However, it's thought that the outer edge of the solar system, as defined by the limit of the influence of the solar wind, is roughly 4 times Pluto's distance from the Sun. That is about 200 astronomical units. So 200 times the distance from Sun to the Earth marks approximately the limit of the solar system. That's also called the heliopause. It's kind of like where the influence of Helios, which is the Sun, pauses or ends. And the solar wind, by the way, which kind of is one of the manifestations of the Sun's influence, is just a stream of charged particles which is emitted by the Sun and can be detected in interstellar space. So, yeah, the solar system actually is mostly empty in that sense, or at least as far as we know, because the last 150 AU away from the Sun, which is still sort of part of the solar system, as far as we know, doesn't have anything in it. Although that's probably wrong. We probably just haven't observed what's in there yet. And there are a lot of theories or hypothetical speculations, or whatever you want to call them, about undiscovered planets or even dwarf suns and all sorts of interesting things that could be there, but we just don't really know at the moment. Another hypothetical object, which has a bit more support than those things I just mentioned, but still has not been directly observed, is called the Oort cloud. It's a very strange spelling. It's spelled Oort, the Oort cloud. It is this spherical cloud of something like 1 trillion icy little objects, which exists really well beyond the edge of the solar system, approximately 50,000 AU away. That's around 1 light year, or the distance that light travels in a year. So these little icy objects are basically the nuclei or the core of comets, which are those things you see or you might have seen streaking across the sky every now and then. They're basically little balls of ice and rock, generally quite small, only a few kilometers across, much smaller than many asteroids are, or much smaller than the largest asteroids anyway. This Oort cloud is thought to be sort of the home or the origin point of many of the long period comets that come into the solar system. For example, something like Halley's Comet, which only comes in around every 80 years or something. Now, the great distance that this Oort cloud is supposed to exist from Earth is really just hard to get your mind around. I said that the outer limit of the Sun's influence is probably only around 200 AU. The Oort cloud, if it exists, probably is about 50,000 AU from Earth. So that's about 200 times further away than the heliopause, or the end of the Sun's influence, and about 1,000 times further away than Pluto. We currently have a probe that's on its way to Pluto. I think it's going to take something along the lines of 10 years to get there in total. I think it was launched around 2006, or 2000, something like that. And it's got a few more years to go before it reaches Pluto. So, and that's one of the fastest probes we've launched. So say takes about 10 years to get to Pluto. That means that it would take 10,000 years to get to the Oort cloud. So that's a very long way away. And That's not even as far away as the nearest stars are to Earth, which brings us now into the next category of extrasolar stars and planets. The closest star to Earth is called Proxima Centauri, and it's just about 4 light years away, so that's around 200,000 AU, so 4 times as far away as the Oort cloud is. So that means that our fastest probes would take about 40,000 years to get to the nearest star, which is 200,000 times as far away from the Sun as Earth is. That's a very long way. So you can see that something like Star Trek, or other sci-fi, where you have adventurers and ships going from planet to planet, star to star, and moving across space like that, is a very, very long way away. Its space is just so mind-bogglingly huge that the distances are just ridiculously enormous. Only 11 stars are known to exist within 10 light years of the solar system. Light year, again, is the distance light travels in a year. It is equal to approximately 50,000 AU. So within 500,000 AU, only 11 stars are known to exist. There's not that many. And out to about 100 light years, about 15,000 stars are known to exist. So 100 light years is probably, at the moment, current theories in physics state, and so this is widely believed, that it's impossible to travel faster than the speed of light. And so even if we somehow did greatly improve our spaceship technology so that we could get near to the speed of light, it seems that, anything even approaching a human lifespan, the maximum you could travel is probably around 100 light years, and so that leaves about 15,000 stars open to us. I mean, 100 light years is still a long way away, and 100 years is a long way to travel, even if you could travel at the speed of light. But the point is that even if you go out to 100 light years, there still aren't that many stars within that distance. Of course, and 15,000 stars is only a tiny fraction of the total size of the Milky Way Galaxy, which is the galaxy in which our star is located. Our star is called Sol, by the way. S-O-L is the correct name, which is why we say the solar system, the system belonging to Sol. Now, our star, that is Sol, is located in a minor spiral arm of the Milky Way Galaxy, called the Orion Cygnus Arm. Now, the Milky Way Galaxy, I'm sure you've seen pictures of it, looks kind of like a whirlpool or a cyclone spiraling into itself, and it has a core, a dense region at the center, which is sort of packed with many stars very close together, and that sort of bulges up to the top and below, and sort of sticking out from the middle are these arms which curl around. So in that sense, it's kind of like a cross in shape between an egg with the yolk sticking out the middle and then the white part around the edges, and a cyclone in terms of the spiraling clouds. It actually looks surprisingly like a cyclone. And the reason that it kind of looks like a cyclone, in fact, is because it's rotating like a cyclone is. And so that produces the twirling of the spiral arms in a sort of a similar way. The Earth, as you know, is gravitationally bound to the Sun, meaning it's attracted to it. Everything in the solar system is gravitationally bound to the Sun. The Sun itself, however, is not gravitationally bound to anything within the Milky Way Galaxy. It's bound to the galaxy itself, or more particularly the core of the galaxy, which is where most of the mass is located, but it's not bound to anything else in the galaxy. So kind of the next unit up from solar system is really the galaxy, and that's often where a lot of people shift to, solar system then galaxy. But there is actually a massive size difference between the two. So, for example, I said that within 100 light years of Earth, which is still a fair way, there are 15,000 stars. But within the galaxy as a whole, there are something like 400 billion stars. That's billion with a B. And probably about 50 billion planets, and maybe many more. So, literally hundreds of billions of stars, and only a few thousand of them are within anything close to travel distance of us, unless we discover something along the lines of wormhole or warp technology or whatever that allows us to travel faster than the speed of light, but that's probably not that likely. So the galaxy itself is about 100,000 light years across, and the Orion Cygnus arm that we're in extends about 10% of the way across the entire galaxy, so it's a fairly large portion of the galaxy, but 100,000 light years is an incredibly long way. If you remember that 1 light year is about 50,000 AU, that means 100,000 light years is about 5 billion astronomical units. So from one side of the galaxy to another is about 5 billion times as far as the Earth is from the Sun. So that's a very, very long way. Another way of putting it is even if you were traveling at the speed of light, it would still take 100,000 years to cross the galaxy. The Sun lies about 25,000 light years from the galactic center, so we're sort of halfway out into the into the rings. And it's actually the sun is rotating, or I should say orbiting, about the galactic center at about 220 kilometers per second, which means it completes one revolution about every 250 million years. So that means 250 million years takes you back approximately to when the dinosaurs were just coming onto the scene on the Earth. So since the beginning of the dinosaurs, the sun has orbited the galaxy only once. So that's sometimes called a galactic year. So those are very, very long indeed. All the stars that you can see in the night sky, at least without a very powerful telescope, are part of the Milky Way Galaxy, because there are stars in other galaxies, but those are far too far away to see with the naked eye. And in fact, not only that, but all the stars you can see with the naked eye are very close, probably within a few hundred light years of us, or maybe less. So almost all of the rest of the stars in the Milky Way Galaxy just appear as a sort of a hazy band of white light that arcs across the celestial sphere, and that's what we call the Milky Way in the sky, because it looks kind of milky. At the center of the galaxy is, as I said, it's a very dense bunch of stars. Many of them are old stars, not very interesting by all accounts. They probably don't have planets because their orbits they're probably too close to each other. So if there was a planet there, the orbits would be all mucked up and the planets would be spun into a star or spun out into the rest of the galaxy or something like that. So there's probably not that much of interest there, except for the fact that we do think, and pretty direct evidence has been discovered now, that there is a supermassive black hole located at the center of the galaxy. Supermassive meaning that it's the mass of millions or even billions of normal stars. So that's a very big black hole. I haven't really talked about black holes on the podcast yet, but a black hole is an extremely dense region of space that's formed from the collapse of a large star. And they're the ones that sort of suck in matter and light from around them, and that you can never escape if you get into them. And it's now thought that most, if not all, galaxies have supermassive black holes at their center, and they kind of form the central gravitational point in the galaxy that everything else is attracted to. So even if you could get to the center of the galaxy, which would take an awful long time because it's so far away, you probably wouldn't want to, because there's nothing much interesting there except getting sucked in a black hole. Just to give you a bit more of an idea of the size of the Milky Way Galaxy, if we reduced the solar system out to the orbit of Pluto, so that's 50 AU, if that was reduced to the size of 1 US quarter, which is about an inch in diameter, or 2.5 centimeters, for those of us who've progressed to the metric system. So if the solar system was the size of a quarter, the Milky Way Galaxy would be about the size of France. So you think of a small coin in France, just on the ground somewhere in France, and that's basically the solar system inside the Milky Way. So we are tiny in comparison to the entire Milky Way Galaxy. That's one reason why many people think it's very likely that intelligent life does exist out there somewhere in the galaxy, because it's just so huge. Interestingly, the number of stars in the Milky Way Galaxy is approximately the same, around the same order of magnitude, as the number of neurons in the human brain. So there's an interesting fact for you. One more point I'd just like to mention about the spiral arms around the galaxy. The reason that they're so distinct and sort of bluish in color is because they are sites of very rapid star formation, particularly large blue stars. And so that's why the arm structures can distinctly be seen, because lots of new stars are being formed there, and so they're all bright, and you can see the clouds that are collapsing into stars and so on. So that's the galaxy. Now we zoom out to the next level, which is called the local group. The local group is a group of galaxies that includes the Milky Way and about 30 other galaxies. So not that many galaxies, around 30. Most of these galaxies are dwarf galaxies, so they're much smaller than the Milky Way. The other big one in the local group is the Andromeda Galaxy, which is actually even larger than the Milky Way. And the Milky Way and the Andromeda Galaxy are actually moving towards each other, and I think in some number of billions of years' time they will actually merge with each other to form one mega galaxy. But anyway, the Andromeda Galaxy is something like 2 million light years away, and the local group itself covers a distance that is a diameter of something along the lines of 10 million light years. So remember that Milky Way itself is only about 100,000 light years across, so the local group, our local little group of galaxies, is about 100 times the size of the Milky Way, so still significantly larger again. Now, it's thought that the Milky Way Galaxy is itself moving about 630 kilometers per second relative to some relevant local frame of reference, which I won't really try to describe, because it's rather complicated when you get to such large scales as to how you define movement, because there's no such thing as absolute frames of reference, as Einstein has told us in relativity, so motion is always relative to something else, and so it's not easy at these scales to pick out what the something else is. But anyway, the Milky Way is thought to be moving about 630 kilometers per second. And remember, the Sun is moving about 220 kilometers per second around the center of the galaxy. And in turn, the Earth is moving at about 30 kilometers per second around the Sun. So even though you think that you're sitting still, in fact, you're moving on a very fast planet, moving around an even faster Sun, moving around an even faster galaxy. So we're certainly not staying still in any absolute sense. Now, the Milky Way Galaxy is located in a group of galaxies, which is something that has, on the order of a few dozen to maybe 100 galaxies. But there's also a larger sort of grouping, which is known as a cluster of galaxies. These contain on the order of hundreds to thousands of galaxies. So they're not formed of clusters, they're like bigger versions of clusters, really, just bunches of galaxies, hundreds of galaxies, gravitationally bound to each other. There's no real sharp dividing line between clusters and groups, it's just clusters are bigger than groups. Interestingly, in many clusters of galaxies, most of the mass, something like 90% of the mass, is not actually in the galaxies themselves, but it's in the form of very high temperature gas, clouds of gas that are located between the galaxies. And it's just being increasingly understood just how important these very high temperature, massive clouds of gas and plasma are, and the role they play in the universe. So, zooming up from the local group is the next unit of measurement, which you probably haven't heard of before. It's much less well known than, say, the galaxy or the solar system. It's called the Virgo supercluster. A supercluster is basically a cluster of clusters. A supercluster will contain something on the order of hundreds, maybe thousands of galaxy groups and clusters, which in turn contain dozens to thousands of galaxies. And within about 100 million light years, there are about 100 galaxy groups and clusters. So remember, the local group itself covers something like a 10 million light year diameter, which is about 100 times the diameter of the Milky Way, and the Virgo supercluster in turn has a diameter of something like 100 million light years, so that's about 10 times the size of the local group, and it contains hundreds of galaxy groups and clusters. And it probably contains tens of thousands of individual galaxies and hundreds of trillions of stars. So, although I'm talking about hundreds of groups and clusters, bear in mind that each of those in turn has hundreds to thousands of galaxies, which in turn has billions of stars in it. So we're talking massive numbers of stars. The Virgo supercluster is a fairly typical sized supercluster. Many of them are actually much larger. At its center is a particularly rich galaxy cluster called the Virgo cluster, which is what the supercluster is named after. And this cluster is surrounded by filaments of other clusters and also sort of lone galaxies that are out there. The local group is located on the outskirts of the Virgo supercluster in a fairly small filament. So we're kind of on the suburban outskirts, if you like, of the supercluster, with the big Virgo cluster, the sort of the city center in the center of the cluster, the supercluster, excuse me. So that's the Virgo supercluster, which is about 100 million light years across. The next stage really is the observable universe. Now, on the largest scale, maximum zoom out, the universe appears to be a collection of giant bubble-like voids separated by sheets and filaments of galaxies, which have galaxies and superclusters, being particularly dense regions of these nodes and sheets. So basically, the universe is spongy, a very sparse sponge on a very large scale. It's full of holes and voids, surrounded by filaments of galaxies and clusters of galaxies. The observable universe is thought to contain hundreds of billions of galaxies and millions of superclusters. So remember that supercluster we talked about, the Virgo supercluster, which is 100 million light years across and contains trillions of stars? The entire observable universe contains millions of those. And the age of the universe is about 13.75 billion years. So that's only several times older than the age of the solar system, actually, which is interesting. However, that doesn't mean that the universe is 13.75 billion light years in radius. Now, the total size of the universe is a bit complicated, because, first of all, we can only see as far away as light has had time to travel, which means the oldest light we can see is light that was first emitted about 13.75 billion years ago, because nothing travels faster than the speed of light, so we can't see anything that's further away than that. However, since that light was emitted, the universe has been expanding. That's what Hubble discovered in the 1950s. So the size of the universe is actually the current diameter of the observable universe. That's what we can see. is estimated to be about 90 billion light years. So that's the diameter from one side to the other. The radius is half that, about 45 billion light years. So if the universe is on the order of 100 billion light years across, that means that our supercluster, which is approximately 100 million light years across, forms approximately 0.1% of the size of the universe. So even that massive supercluster, which contains hundreds of clusters and groups and tens of thousands of galaxies and hundreds of trillions of stars, is only 0.1% of the universe. Not even 0.1% of the number of clusters in the universe, but just 0.1% of the distance across the universe. And there are millions of other superclusters out there. So the universe is enormous. 100 billion light years, almost an inconceivably huge distance. But that might not be it. Because, as I said, we can only see as far as the universe has had time to reveal to us, basically, because you can't see further than we can't see further away than the distance traveled by light since the universe was created about 13.75 billion years ago. But if the universe has expanded faster than the speed of light at some point in the past, which is thought to be the case, in fact, it's thought that the universe expanded much faster than the speed of light, and look back to the Origin of the Universe podcast for more details on that, then that means that the total universe would be much, much larger than the observable universe. In fact, it's thought that it's the unobservable universe, the entirety of space and matter created by our Big Bang, is probably many orders of magnitude, maybe dozens of orders of magnitude, larger than the observable universe. So goodness knows how large the total universe is. But it probably doesn't even stop there, or at least may not even stop there, because many current theories in theoretical physics and cosmology, and there are a number of different types of these theories, string theory is sort of related to this, as are other theories of cosmic inflation, propose that there are a large number, and perhaps an infinite number, of other universes existing totally separate from our universe. That is, totally separate even from the unobservable parts of our universe. These could have been created by other Big Bangs, or even by having completely different laws of physics and created by completely different means than our own universe. So goodness knows what these sort of parallel universes might look like. And if it's true that there's an infinite number of these universes, then that means that there is also an infinite number of other universes in which I am also recording exactly the same podcast, or exactly the same podcast but with one word differently. And there is also an infinite number of universes with you listening to this podcast, or you listening to this podcast but on a different day. But of course that's only if you believe in these theories that say there are an infinite number of universes. Personally, I think that the infinite might be going a bit too far, but I do think it could be quite likely that there are large numbers of other universes existing outside of our own. However, even if you don't like those parallel universes concept, it is much more likely, so it's much more solid, that there is space outside of the observable universe that we can never have access to. However, that space is probably very similar to our own sort of universe, and there probably aren't copies of you there. So, that is the universe, right from the Earth's place in the universe, right from the Earth and the solar system, up through the Milky Way, the local group, the Virgo supercluster, and the universe as a whole. Now, to summarize that, I've heard a quote something to this extent, and I'll just sort of paraphrase it for you, that the Earth is a fairly average sort of planet, orbiting a very ordinary star. The Sun is a G-type star, which is a very common type of star in the galaxy. So the Earth's orbiting a fairly ordinary type star, which is located in a fairly ordinary location, not particularly interesting, not particularly special location in the Milky Way Galaxy, which in turn is a fairly ordinary sized galaxy in a fairly mundane section of what is a relatively small and insignificant supercluster in a not particularly important section of the universe. Contrary to earlier points in history where it was thought the Earth was the center of the universe, there's actually nothing at all special about the Earth in terms of its location in the universe, the galaxy it's in, the solar system, or anything, except for the fact that it is currently the only planet, or the only place known in the universe to be home to life, and that certainly is very special. However, I certainly hope that in the near future that will no longer be the case, and we'll find life somewhere else. However, there's one other point that I'd like to make. It's actually true that the Earth is the center of the universe, because remember that if you define the universe being the observable universe, then we can only see things that have had where the light has had time to reach us, and that means that we can see out to 13.75 billion light years in every direction. Now, it's actually further than that because space has expanded in the meantime, but you get what I'm saying. The distance we can see is the same in every direction, isotropic, sort of. Which in turn means that the Earth is the center of the universe. The only downside of that is that every other place in the universe is also the center of the universe, or the center of its observable universe, because every place in the universe can see different parts of the universe. So, unfortunately, we are unable to recover a special location for Earth in the universe, even though we kind of are the center of the universe, because everywhere is the center of the universe. And so that's all I have to say for this podcast. Hope you enjoyed it. I'm your host, James Fodor, and please leave a comment if you enjoyed this podcast on the podcast website, which is fods12 at pod.podbean.com, or you can leave a comment on iTunes, which I'd appreciate, a rating, and share this podcast with your friends if you enjoyed it and want to expose them to some science learning. And until next time, goodbye.